Good day, everyone! So, for today's activity, we were given the task of making a detailed presentation on our chosen laboratory activity, which we decided as a group to be the dumb coin experiment. We'll perform an experiment using coins, water, and surface tension in this presentation. If you want to take part, you will need a water dropper, cup of water, coins of various sizes, and a pen and paper. The materials list will be shown later. So we conducted a simple test to determine the different amounts of liquids a penny can contain in this activity. As you may have observed, we'll be conducting this experiment using coins of varying sizes in order to see how one coin compares to others. You might also ask why or what causes the water to spill over your coin. That's because surface tension is what causes the water drops to form in a dome-like shape on the surface of your coin. More tension is formed with each droplet, resulting in a greater force of attraction between the water molecules. The water will break the surface tension and spill over the coin once it reaches the limit. You'll probably learn through this activity that a coin with a larger size is more likely to have a large amount of drops. The reason you can get so many drops of water on a penny is due to surface tension and cohesion. The stickiness of similar molecules to one another is referred to as cohesion. Water molecules have a strong desire to stick together. Now, without further ado, let us now present our experiment to discover more about it.
Materials. We use a mug instead of a cup because we don't have a cup available and fill up with water. Set out the coins on a complete flat surface. We fill out the chart with the number of drops of prediction on each coin. We write different numbers on each coin. We depend the number of prediction of drops to the size of the coin. We begin in a 1 peso coin and putting 1 drop at a time. In a second time, we use again the 1 peso coin. 1 peso coin in a third time. We find the average number of drops of a 1 peso coin, so we add the actual drops and divide it by the number of the times we use the 1 penny coin, which is 3 times. So we have 35. In this time, we use 5 peso coin. Remember, 1 drop at a time. For the second time, we use again the 5 peso coin. For the third time, we use again the 5 peso coin. For 5 peso coin, we have an average of 44. And this time, we use 10 peso coin. Same as 1 peso coin and 5 peso coin, we try it 3 times. So we have here that 10 peso coin average is equal to 56.3. So we rounded out the 56.3 to the whole nearest number because it is not possible that your drops is in a decimal form. So we have 56.
When we try with other coins, how does it differ? During the demonstration, we have noticed that the droplets of water will stick more on a big coin, and it also depends on how we drop the water on the coin. If you flick it quickly, the water stays in one place and then drops into the coin. An object at rest will remain at rest. Furthermore, the number of droplets of water become bigger. It depends on the size of the penny.
Do all pennies hold the same amount of water? The answer is no, in which all penny doesn't hold the same amount of water due to the reason that they do not have the same sizes. The results indicate that when you drop water on a penny, that the head side of the penny will hold more drops, in which as drops of water are added onto a penny, the adhesive force between the water and the penny keeps the water from pulling off. Cohesive forces are strong but not unbreakable. As a water drop builds up and out, usually bulging over the sides of the penny, the cohesive forces will eventually be overcome by the force of gravity on the water molecules. The skin will burst and all of the water will spill off. What variations do coins have that allow one to hold or more or less than the other? Once the water has reached the edge of the penny, a dome shape begins to form. This is due to the surface tension forming a shape that has the least amount of surface area possible. It is also how the length at which the water drops the coin. The farther the drop it takes to go to the coin, the higher the impact and makes it different in the number of drops.
What other things besides affect the number of drops?
The distance between the dropper and the coin, which is the distance between the dropper and the coin, just like what do, will probably affect the number of drops because you cannot control where the water drops from the coin. It seems like water split from the coins because the distance between the dropper and the coin is far away.
Conclusion: cohesion is a term of attraction between water molecules. As a result, we conclude that the cohesive force between water molecules is so strong that it forms a skin at the water's surface tension. However, cohesive forces are powerful but they aren't unbreakable. So the cohesive force on the water molecules will eventually be overcome by a gravity as a water drop develops up and out. On this experiment, we seems like challenged to observe the power of surface tension in the water droplets, despite the fact that a water molecule has an overall neutral charge since it has positive and negative end. And there is adhesion, which is attraction on the type of molecule to another type of molecule, and it may be fairly powerful of water, especially when combined with other molecules that have positive and negative charges. So again, once the water has reached the penny's edge, a dome shape begins to develop once more, and also the amount of water droplets increase in the proportion to the size of the coin.